Understanding Chromatographic Selectivity, which is part one of a three-part series titled A Systematic UHPLC and HPLC Method Development Strategy with Complementary Stationary Phases to Maximize Selectivity and Resolution. My name is Alex Nase from MacMod Analytical, and I will be moderating today's webinar. If you do have any questions during the presentation, please type them into the chat and include your name and company. We will do our best to answer as many as possible in the Q&A portion at the end. If you miss anything or would like to review the content, we'll be sending out a recording as well as the slides in a follow-up email at some point, either at the end of this week or early next week. You'll also find a collection of our past webinars and resources on MacMod's website. MacMod is a chromatography company that offers scientists innovative solutions for their complex separation needs. We recommend and supply the best columns and accessories to our customers, and we also provide application notes, technical reports, white papers, and other up-to-date resources from industry-leading scientists to keep you informed. Today's speaker, who I actually have been working with for almost 15 years now, is Gemma Lowe. Gemma is the global portfolio manager at Avantor, based in the UK, and is responsible for the self-manufactured chromatography portfolio, which includes HPLC, UHPLC, GC, TLC, and sample preparation columns and workflow solvents. Gemma has over a decade of experience working in the high chrome technical support team, troubleshooting chromatography methods, recommending suitable column chemistries, and supporting the vast range of chromatography columns. Additional experience in HPLC column manufacture and business development are used to support the portfolio. Originally a biochemist, focus areas include the analysis of biomolecules and polar analytes by various chromatographic techniques and working in close collaboration with the Avantor R&D and applications teams. Thank you for joining us today, Gemma.
Thanks, Alex, for the lovely introduction, and it's been a pleasure working with you for the past 15 years. So yeah, nice to add that in. So hello, everyone. Thank you for joining us for today's webinar. As Alex mentioned, we're going to be talking about chromatographic selectivity, and this is part of 3 sessions we're going to run over the coming weeks. So today we're going to look at why selectivity is important, specifically in reverse phase chromatography from both a theoretical and a practical point of view. We're going to have one very brief look at the end at method development workflows, but more of that to come in subsequent sessions. Before I start, I want to say a very big thank you for inviting me to speak. We've been working with MacMod for a long time, and they are a great partner to work with, very technical, talking about columns that are going to solve your problems. So we're going to jump straight in and talk about selectivity. And I really wanted to put this early slide in so we're all grounded on what I mean by selectivity. I know there's a small amount of maths on here, but it's really important to understand how selectivity fits in. And in terms of chromatographic selectivity, sorry, I'm trying to find my mouse, it's disappeared, here we go. In terms of chromatographic selectivity, what we're trying to do is separate peaks. Not many of us are lucky enough just to have one analyte of interest. We're generally trying to pull those peaks apart. And selectivity is a measure of peak spacing. So it's sort of describing how far apart those peaks are. And chromatographically, the data system is using these formulae to work it out. So what you need to know is the T0, which is a measure of the dead volume of the system. And you need to know the retention time, so the TR of each of the peaks. So here you can see we've got 2 sequential peaks. they've got 2 separate retention times, and they are not eluting at the same time, which is great. That's what we want to achieve. So we can work out a K value, so a retention factor, based on that TR and the T0 using the top calculation. And then we can work out a selectivity value based on the ratio of K values for 2 sequential peaks. We want that number, that alpha value, that selectivity value, to be larger than 1, because if the retention times, or the retention factors, sorry, for those 2 peaks are the same, then you have 1, alpha equals 1. They only need to be slightly separated to be greater than 1 and to give you an alpha value over 1, showing you've got baseline, or you've got a separation between the peaks. Alpha is very important when we're talking about our method development. It's something we should really consider. It's not the only factor that's influencing resolution, though, and resolution is often what we're having to report in our methods. So how does that fit with resolution? So here we have another equation. I'm going to go through it quite simply and practically to show you what this means in real life. So resolution, as I've said, is what we normally need to report out in our methods. And ideally, we want that value to be 1.5 or higher, which is showing a baseline resolution of 2 peaks. Ideally, you want to kind of aim for 2 if you can when you're starting your method development. Sometimes you can't get that high, but so 1.5 is at least the first peak touching the baseline before the second peak starts. So the resolution is made up of 3 sort of parameters: an efficiency part, which is shown here in blue, the selectivity, which I've already mentioned, and then the retention factor, which I also mentioned when we looked at the first slide. Now, they don't have an equal weighting within this resolution equation, and you can see that really in the right graphic. So you can see here, color coordinated, that each of those 3 parameters has a different influence on resolution. So in my graph here, I've got resolution on the y-axis, and I have those 3 parameters on the x-axis. You can see retention factor, so the K, the green graph, looks a bit like a reaction curve. It's important initially to have good retention, but when you get past sort of 5 or 10, it's the law of diminishing returns. You don't get anything back for having larger retention factors. Efficiency is more powerful, so it's a steeper curve, and the more efficient your system, your column, the higher the resolution. So you could have a longer column, you could use a smaller particle size, but if you go back to this equation, that is a square root term. So it takes a lot to achieve double the efficiency, for example. So the most powerful tool, and what we're really focusing in on today, is the alpha value, this red curve, and that is the measure of selectivity. And you can see from the x-axis that you only need a very small change in selectivity to achieve a very large change in resolution. So selectivity is key, and then you can improve or boost the performance by looking at the efficiency. So it's really important to know what affects selectivity. Now, that's not only when you're doing method development, but also if you want a consistent, reproducible, robust method, because anything affecting selectivity is going to move your peaks around. And therefore, if you're not controlling those factors affecting selectivity, then you could get inconsistent chromatography run to run, day to day, because one of these factors is not under control. So what we've done nicely here is put the factors affecting isocratic separations on the left-hand side of the screen. And we have put I don't want to highlight it, I want a laser. So on this left-hand side of the screen, you can see those factors affecting isocratic. If you're running a gradient method, so you're changing the percentage of organic, then you also have to consider some additional factors which are shown in this box on the right-hand side. And we've nicely put them in order of the most influential factors. So the biggest way to change selectivity in your chromatographic method is to change the column stationary phase. I am not really going to talk about that today. I'm going to talk about that next time. I'll have a quick preview, a couple of slides, but generally that is the biggest way to change your selectivity. If you've got ionizable analytes, pH is really important. That's going to have a massive influence. Most of us will have ionizable compounds in that mixture. Then you've got the modifier, so the organic modifier, the type and the percentage. You've got which buffer you choose, what temperature you choose, and also how much buffer. When you're running a gradient method, you also have the gradient factors to think about. So how steep is that gradient? You know, some types of molecules prefer a shallower gradient. Some prefer a steeper gradient to give you improved selectivity. There's also this retention factor K star in a gradient method, and that takes into consideration the gradient time, the flow rate, the gradient range, and the column volume. So all of those factors could change the selectivity, and therefore if you've decided you're going to speed up your methods and you scale the gradient, if you don't scale it accurately, you might be changing the selectivity within the system, because all of these parameters affect that alpha term. There's also the instrument dwell volume and the column dimensions, because they impact that column volume. So we're going to touch on a few of these today. I don't have so much time to go into the columns, but we will revisit that next time. I'm going to talk more today about the mobile phase choices and one slide on temperature as well. So just very quickly on columns, I've said they're the most influential change on alpha. And even when you buy a C18 from a different vendor, it could still have a different selectivity compared with your existing C18. So they're all listed as C18, but when we manufacture these columns, there's different end capping, different pore sizes, different pore shape. There's different carbon load, different surface area, and all of that will have an impact on the selectivity, and therefore the retention is slightly different, the selectivity is slightly different, even when you have the same bonded phase. So C18s are all similar, and actually if you look at the elution order, everything is kind of eluting 1 through 16, 1 through 16, but you can definitely see peaks moving around. It's not really a significant change in selectivity if you just use a different vendor's C18, but if you go to some of the other bonded phases, then you start to see real differences in selectivity, in alpha, in the peak elution order, in the peak shape, and sensitivity as well. So here's my little taster. Come back for part 2 and we'll talk a bit more about column chemistries. What I want to focus on in the last section is what you can do with your mobile phase really to change alpha or to keep it consistent. So pH has a massive influence. It really is important to consider using a buffer and make sure that it's buffering within that correct pH range. It could give you better selectivity. It could give you worse selectivity. If you don't control it, then you're running that risk of non-repeatable chromatography. So here's an example of looking at different buffer types. So here we've got a very simple mixture, 2 analytes, isocratic method, and we're just adding a different buffer in each case. And you can see low pH with TFA. I can't even tell you if there's 2 analytes there. And the same at pH 3 with ammonium formate. It's challenging to say there's 2 analytes in that mixture. Changing to ammonium bicarb and elevating the pH up to 7, now you've got massive resolution. Really significant change in selectivity by changing the pH and the buffer. And obviously you have to change the buffer to be working within the right pH range. You can see here pH 10 with ammonium hydroxide changed. Oh no, sorry, this is still the same buffer. This one's ammonium bicarb at pH 10. So all I've done is change the pH, but I've changed the retention time, I've changed the resolution, I've changed the K value, I've changed the selectivity. And here we've changed to the ammonium hydroxide. And again, you can see a big difference. You can see the peaks are starting to get a bit broader. The retention time here is probably a bit too long. K values are too high. But it shows you the influence of changing pH on a very simple mix of bases. Now, working near an analyte pKa can be pretty problematic, and you'll see this. You kind of know in your chromatography whether you are near an analyte pKa if you see these big differences when you have very small differences in pH. So here, got a pH 2.2 going to pH 2.3, and hand on heart, how well do we make up our buffers? What's the accuracy? Could that first one be pH 2.25, you know, and then the next person makes it up and it's 2.20 or 2.19? So very small changes in the buffer in this case have led to massive changes in resolution for these later eluting peaks. First couple of peaks not so influenced by the change of pH, but these later eluters have really changed in resolution based on the change in pH, 0.1 pH units. And that's, you know, it's an error. You can easily make that error in the lab. So the way to avoid this is to look at your design space, try making things up a little bit incorrectly and see if you're on the knife edge of the pH. This is not a robust method in this case. And again, I've got another one here. So you can see it's not an isolated case. This is looking at benzoic acids, and the difference of 0.1 pH unit has completely changed the resolution of one of these, of this critical pair here that was nicely baseline resolved at 1.7 at pH 2.9, but is co-eluting by just shifting that 0.1 pH unit. So make sure that you do explore that pH space during your method development. The other thing to think about is the mobile phase composition and which organic modifiers you use and how much of them. They have direct impacts on not only selectivity, but also retention and efficiency as well. And if you're running an isocratic method, you will see a nice linear relationship between the percentage organic and the retention time. So for isocratic methods, it has a nice clear relationship with the organic percentage organic. We tend to use methanol, acetonitrile, IPA, THF as our modifiers, as our organic modifiers in reverse phase chromatography, and they have different interactions. We choose these to give us different selectivity. So when you're exploring your method development, it's worth looking at solvents that have different proton acceptors and donors and dipole interactions to make sure that you're exploring that selectivity space. When we look at the solvent strength, you can see they also have a different strength. So for example, if I want to run the same method with acetonitrile and switch it to methanol, I have to use a different percentage. However, you'd think that was a nice switch. We just switch, we do 10% more. Doesn't quite work out that way because of those differing interactions. So when you switch between methanol and acetonitrile in this case, but you match up the solvent strength. So we tried this when there was a acetonitrile shortage, for example. We tried to move the methods onto methanol. So the equivalent of 40% acetonitrile is 50% methanol, which worked fine for peaks 1 to 3. Look at the difference in resolution between the final 2 peaks. It's really massive change in alpha, change in selectivity. If this was our original method, then happy days. Now I've switched it to methanol and I'm really happy. If it was the other way around, it's a bit of a problem. So it's always worth looking at different concentrations. This is again just looking at acetonitrile water mixtures and how you can get different alpha values, different selectivity as you change the percentage organic. And you can also use modeling software to support this kind of work as well. Here we can see when we go up to 60% aqueous in our mobile phase, we've got really poor resolution of the last eluting peaks. But if you go back to 50-50, those peaks look great. You've got a problem with peaks 2 and 3. So somewhere in between, somewhere up here, gives you much better chromatography. There are changes in selectivity if you look at the peak spacing versus different percentages higher up the chart. And then a more complicated example here is just showing, here we had 3 APIs in the mixture, so you've got some really heavily overloaded peaks. You've got lots of critical peak pairs, but switching between acetonitrile and methanol, even on the same column, you can see significant differences in alpha. And then if you add in a column, chemistry as a factor there as well, then you get even more differences and a wider selectivity space to explore. In this case, we saw that methanol provided better retention and selectivity, specifically for these earlier eluters, so the more hydrophilic analytes, but it's dependent on what your mixture is. Sometimes acetonitrile will be way better than methanol. The final thing I just wanted to mention briefly was temperature, and temperature sort of mimics pH a bit in terms of it can change the charge on analytes, and therefore if you change temperature, which is obviously quite an easy thing to change on the instrument rather than having to make up a new mobile phase or switch the column out, if you play with temperature and optimize the temperature, that can also have beneficial effects on your selectivity. It can be detrimental as well. I've seen some examples in the past where people weren't controlling the temperature and then peaks were moving around and you're getting inconsistent chromatography. So make sure that the temperature is preset and it is working properly. I've definitely seen some problems where ovens are not delivering what they say they're delivering. But you can see even peaks swapping around in elution order, big changes in selectivity just from playing with the temperature. So finally, kind of putting it all together and maybe a bit of a glimpse for the next webinar, in terms of workflows and how you want to do your method development, it's good to pull all of these parameters in that impact selectivity. So type of column, temperature of column, pH, organic modifier, and then something I didn't sort of dwell on, but the gradient time. So we will look at that in more detail next time. Some of the resources we have available for you, and you can download for free on MacMod's Resource Center, information about different buffers, different how you measure K values, and also information about controlling pH. I thought these might be relevant to what we've talked about today, and hopefully useful resources for you to come back to when you're exploring alpha based on these parameters. And then finally, if you do have any questions, I've put my email here. Please do feel free to reach out to me. Alex also kindly offered to have his email on this slide. So please also, if you have questions, speak to Alex and one of us can support you. And with that, I'll see if there are any questions in the chat, please, Alex.
Thanks, Gemma. That was an incredible presentation. I mean, I can say we've been talking about selectivity with you and HiChrome and Avantor for many, many years now. So she is an expert on this subject. So if you do have a question, please put it into the question box and we will move on to the Q&A. So first question, can I use acetonitrile with a PFP column?
Great question. And you probably saw some examples of us using acetonitrile with a PFP column through the presentation. There is some press and some information talking about suppression of pi-pi interactions when you use acetonitrile. We've seen that you get significant differences in selectivity when you switch between methanol and acetonitrile, even with a PFP phase. So they might be more suppressed, but in terms of a method development approach, you're still seeing differences in selectivity that can be beneficial for some analyte mixes. So yes, you can. It's not going to break it. You might not get as strong pi-pi interactions potentially, but yeah, we haven't seen a problem using it with that solvent.
Okay. Could you please name can you talk at all about your silica hybrid particle, fully porous and superficially porous?
From Avantor, we have fully porous and superficially porous particles. We don't have any hybrid particles at the moment, but we do have kind of mixed mode type bondings like the C18 AR and the C18 PFP we saw in earlier slides. You will get different selectivity when it comes to some of those different particle morphologies. And I think we'll probably touch on that a bit more next time. But in terms of things like the carbon load on a solid core particle is going to be slightly different to the fully porous, and that could have an influence on selectivity, for example. So I think definitely those types of products are really good for reducing solvent usage, for speeding up methods, and for improved efficiency sometimes. In terms of selectivity, a lot of it comes down to the bonded ligand. what the column chemistry is. That's really going to influence moving those peaks around.
You mentioned modeling software. What modeling software have you used?
We've played with a few different softwares. I think we've got one that we work with in-house that's called Chromatographic that works pretty well. We've loaded our columns in there, and so it kind of predicts it predicts well. So the predictions look like our assays. We've also used software like DryLab. That one's been good to us over the years, and that's interesting for temperature modeling as well. We've done some more temperature modeling on that. We've used some other sort of, lots of softwares, to be honest, in the past. Those are the two that we use the most in-house in our kind of R&D lab.
Okay. What type of particle is the A6L Super C18?
So the A6L Super C18 is we've got that on fully porous or superficially porous. We've got that with two different particle morphologies, and then they're kind of coated particles that make them more stable at high pH. So there's a coating on the surface that, even though they're silica, they can still be used up to pH sort of 10.5 with LCMS compatible buffers without dissolving. So normal silica will start to dissolve up at those high pHs, but this coating sort of stops that dissolution.
Okay. Are there any other ways to change selectivity dramatically?
You could change the mode of chromatography. So I've focused really today on reverse phase, but of course you could shift completely over to, I was going to say normal phase, but really more people are moving to HILIC, so hydrophilic liquid chromatography. That would give you a real shift in elution order, in retention and selectivity. But then you have to consider that it's a different mode of chromatography. So you need to optimize the system for that mode of chromatography, sort of change wash solvents, think about diluents, etc. So it's more painful as a chromatographer, I would say, to shift away from reverse phase, but you can definitely get good retention for more hydrophilic compounds in that case, and maybe some charged analytes too.
Okay. I think that's all the time we have for today. If you did ask a question that we did not get to, we will follow up with you via email. And we will also be sending out an email after the webinar to everybody who attended or registered that will have a link to the recording as well as the slides from the presentation. If you found this talk helpful, please register for part 2 and 3 of this series. Part 2 is on stationary phase design and will be held at the end of the month on October 24th. Part 3 is on December 12th and will introduce a screening platform for HPLC and HPLC method development. We will also include links to register for both of these follow-up webinars in the follow-up email. Thanks again, everyone, for joining us today, and thank you, Gemma, for a great presentation. Have a great rest of your day.
Thanks.